Welcome back. In this video, we will discuss the first Python script, generate microstructures.py. This Python script requires a handful of other software suites to execute, so we will first review these. The first software package that is required is Python. Users can Google Python Anaconda, which will take you to the anaconda.com website. From here, users can simply click on Download and download one of these versions. Of course, there are many other methods of installing Python, so users should proceed with the one easiest to them. The next software that is used by Prisms-Fatigue is Paraview, which is commonly used in the engineering and scientific communities. This software visualizes complex datasets. The website paraview.org can be used to download Paraview. The final software that is required is Dream3D. Dream3D can be downloaded from the Blue Quartz software website. So if users Google Blue Quartz software, this will be the first link. From here, we navigate to the top to our software. Click on Dream3D, download here. And this takes us to the Dream3D website. Once again, we could click on download at the top, and in this case, I will be downloading it for Windows 64-bit. It will ask you to answer this question, and after you hit download, it will download the software in a zip folder onto your computer. So let's look at that folder right over here. So these are the files that come in a standard download of Dream3D. The two that we will focus on are the dream3d.exe, which is the executable, as well as pipeline-runner.exe, which is also an executable. The version of Dream3D downloaded here is 6.5.141, but the script should be backwards compatible with any recent version of Dream3D. To open Dream3D, double-click on the dream3d.exe executable file. This will open up a blank graphical user interface. In the written tutorial, I've labeled the 6 different regions of this GUI. The basic way to use Dream3D is to first find the filters that you would like to use on the filter list and drag and drop these to the pipeline. The center of Dream3D will then indicate all the different parameters that we can set with this particular filter. Now, I will open up one of the included Dream3D files as part of Prisms-Fatigue, which we will call the input file. The input file I've opened here is entitled AL7075 Cubic Texture Elongated Grains. So this input file will give us a microstructure that has cubic crystallographic texture and elongated grain morphology. Let's first look at the parameters of the stats generator filter. In this first tab here, we specify the different parameters for the log normal grain size distribution. The drop-down here will control the shape of our grains, whether they be equiaxed or rolled. If we choose rolled, then we get this option box for what the ratios must be in the axis length of A, B, and C. This particular file has elongated grains, and if you read the corresponding manuscript for Prisms-Fatigue, you'll see that the grain morphology that we use has an elongation ratio of 5:1:1 in the A, B, C directions. So if we go on the tab of B over A and C over A for the shape distribution, this should give us a lot of spikes near 0.2 because this corresponds to the 5:1 ratio. The ODF tab specifies the crystallographic texture that will be generated in Dream3D. So in this case, we have a cubic crystallographic texture. This is entirely controlled by the lines entered here. So the more lines we enter, the more control we have over our crystallographic texture. The misorientation distribution function tab tells us the misorientation, target misorientation between generated grains. The final tab entitled Axis ODF controls the directions in which the grains are elongated. In this case, we elongate the grains in the a-axis, which corresponds to the x-axis. This is particularly useful for users that want to perhaps simulate the effects of grain elongation ratios in different directions. The final settings of this filter are controlled by this gearbox up here. So here we can specify the crystal structure of our material, whether that be cubic or hexagonal or something more complicated. We can set the phase volume fraction, and we can even pick different types of phases. So in this case, we have a primary phase, we have a precipitate phase on this tab. So this precipitate phase has an entirely different set of parameters. We can also add a matrix phase. One thing to note is that although we have two tabs here at the top, meaning we would have two phases, when we click on the gearbox, we see that the volume fraction of the first phase is 1, and the volume fraction of the second precipitate phase is 0. So even though we have two tabs, we're only going to generate a single phase microstructure with this file. And the associated files we'll talk about in just a second are set up to work with multiple phases of Dream3D. And the way we would do that is if, for instance, we change the fraction here from 0 to 0.2 and hit OK, then this will update the volume fraction of the first phase, and then we have the associated volume fraction of the second phase. So we could change this once more to 0.5, and the way that it calculates the phase fraction is the 0.5 divided by the total fraction we described. So primary phase has 1, precipitate phase has 0.5, so this phase fraction is 0.333 because it's 1/3. And then this would be, of course, 0.667. Once the user has set all the parameters, the next filter, write Dream3D data file, simply saves these parameters to a .dream3D data file. As mentioned, this is what we will refer to as the input file. So it is important to note that once this pipeline is executed, so once we hit start pipeline, first the stats generator is executed, then this filter is executed, and it will create this file. If this file is opened, Dream3D gives an option for the user to see the filters that were used to make that data file. And that's very important because the point of these is to set some type of parameters, click create data, and then to save these parameters to be read in by the Dream3D pipeline that we will talk about next. Additionally, I should note that there are help files for each of these filters. So if we click on help, then Dream3D help, this will open up the Dream3D website. Additionally, if you click on the filters with right click, you can click on filter help, and this will open up help for that specific filter. In the initial release of Prisms-Fatigue, we provide 6 different types of input files. These include combinations of 3 crystallographic textures, along with equiaxed and elongated grain morphologies. If users make any changes to the parameters in the stats generator filter, it is important that they know to hit create data and then to execute this pipeline and save this as a new .dream3D file. What this means is that if a change is made somewhere here, users cannot simply go on File, Save, and expect this to be the updated input file. So we will now discuss the second type of Dream3D file provided to Prisms-Fatigue users. It is entitled Dream3D Microstructure Pipeline. So this is a .json file, which means that we can actually right-click and open this file in a text editor such as Notepad++. And actually, what happens in our Python scripts is that the script generate microstructures.py opens this file as a text file, finds certain lines and edits and replaces them based on user inputs. And the reason we do this is because then we could call Dream3D many times without having to actually open up this interactive GUI and change parameters in the filters. So let's briefly discuss some of the filters in this pipeline. The first one is entitled Read Dream3D Data File. In this one, all we do is point to a pre-existing .dream3d data file, and this will read in information necessary for a tessellation. So in this case, the .dream3d data file only had information about the statistics of a microstructure, and that is shown here on the right. The second filter creates a synthetic volume into which the microstructure will be packed. So we can see here on the right, a new type of data structure is created with this filter. The first line specifies the number of elements in each direction, and the second line specifies the resolution or the size of each voxel. I should note that there is no inherent length scale in Dream3D, so users just have to be careful in terms of knowing exactly what size they want to create. Pack primary phases then puts seeds of grains into the synthetic volume and tessellates or grows them until all the volume is packed. This is where we will start to see different types of data structures on the right. So cell data means that it contains data for each voxel of the microstructure. Cell feature data means that it contains information for every feature or grain. And cell ensemble data contains information for the entire phase of a certain grain. So these next filters further manipulate the microstructure. For instance, find feature neighbors finds all the grains that neighbor one another and stores this information. Match crystallography iteratively swaps grains until the desired crystallographic texture is met. Vtk Grid Exporter actually exports the microstructure to a VTK file for visualization. Export feature data as CSV file exports information for each grain to a CSV file, which includes the center of mass, the Euler angles, the size in terms of a equivalent diameter or number of elements. It also contains information in terms of what grains neighbor one another or what grains exist at the surface of an instantiation, meaning at the boundary. Export DX file is actually one of the filters that exports the information necessary to simulate this microstructure in Prisms-plasticity. These next filters perform the math necessary to export the second text file that we need, necessary for Prisms-plasticity simulations. More specifically, these filters calculate the three components of the Rodriguez vector that is used to represent grain orientations for simulations. This final filter exports this entire microstructure, not just the statistics, as a .dream3d file, which can be visualized but also read in by another Dream3D pipeline to further manipulate the data. So we can see here on the right that now we have a ton more information on this microstructure. As I mentioned, cell data contains information at each voxel, whereas cell feature data contains information for each grain. So in this case, this will contain such items such as the equivalent diameter, the centroid, whether or not the grain is at the surface, which would be indicated by surface feature. The final note with these JSON files is that these can be saved by going to File and clicking on Save, because all we're really changing is the .json text file, whereas the Dream3D data files, as pointed to here, these cannot be saved by clicking File and Save. The grain size that we specify in these .dream3d files is 14 microns, and the synthetic volume that we will specify will be 72.5 microns for each side. So this will give us approximately 250 grains for each microstructure. Let's move on to the Python scripts themselves. First, navigate to the GitHub page for the Prisms Center. You can do this by simply Googling Prisms Center GitHub and clicking on the first link. This will take you to all the repositories and softwares of Prisms. Click on Fatigue. This will take you to the Prisms-Fatigue page, which is still under construction. However, the Python scripts are ready for download in the source folder up here. So if you click on this, you can see all the Dream3D files as well as the 5 Python scripts. Download this using the button here, and you can either do this by downloading all the files as a zip file or by using a GitHub desktop client. So let's examine this first Python script, generate microstructures.py. What I have open here is the script itself in the software of Notepad++. It consists of a series of functions that call one another. At the top of the function, we have these lines that import certain Python packages or modules to execute certain commands. These are very standard packages and they should come pre-installed in any Python download, such as with Anaconda. However, one of the more common errors in Python is perhaps executing a package that is not yet installed for the user. If this happens, users are encouraged to simply Google that package and find a way to install it, which should be very straightforward. The next section of the code defines some conventions for how to save the files that are generated. If we scroll to the bottom, we will find a function called main. So main is actually the function where users will enter all the parameters to instantiate the microstructures. Users first need to create a directory to which microstructures will be instantiated. In this case, we will create a new folder called Prisms-Fatigue_tutorial. And in that folder, we will create another folder called cubic tutorial. So this directory can be set either in this manner, where dir_loc is the location of the generate microstructures script, or users can set an absolute path. The user would then define the location of the Dream3D input file. So this is the .dream3D file that we discussed first, as well as the Dream3D pipeline path, which is the .json file that we described second. The last Dream3D file we need to point to is the file called the pipeline runner that we discussed earlier. So we need to specify this simply because this Python script will actually execute Dream3D as a sub-process. So we just need to let Python know where this file actually is. These next two parameters are size and shape. And once we specify this, Python will actually open the .json file and overwrite the settings in the initialized synthetic volume. So in this case, we have 0.0725, and this will be in millimeters. And we have a resolution of 29 elements in the X, Y, and the Z. Numvox controls the number of elements in each subband region. So we discussed these in the first video, but users are encouraged to go to these references shown at the bottom to get a better understanding of the effect of the number of elements in each subband region on the FIP extreme value distributions. The next setting is numPlanes. So this specifies the unique crystallographic slit planes in the microstructure. In the case of aluminum 7075, which is a face-centered cubic material, there are 4 slit planes. This is required for banding of the microstructure, as shown in the previous video. And this actually refers to this section of the code here, where we specify the FCC octahedral slit plane normal directions. The next setting specifies the face boundary conditions for generating the microstructure and then further pre-processing it, for which we will calculate FIPS. So in this case, we have one of three options. We can set these either all to periodic, we can set them all to free, or we could set two of them to periodic and one to free. And I will go over in just a few minutes what influence this has. The last setting that we have is number of instantiations, and this simply tells us how many different instantiations or microstructures should be generated for this run of generate microstructures. So what this is really useful for is we could set this to 10 or 20 or some large number, and that way we can get many microstructures without having to open the Dream3D GUI and executing it 10 or 20 times. And this will create numbered files that are unique to each instantiation. So now I will demonstrate how to actually execute these Python scripts. What I have opened in the top right is a command prompt window, and on the left I'm in the Prisms-Fatigue folder where I have my .dream3D files. So those are the input files that we have 6 of. The .json file, that is the Dream3D pipeline, and the Python scripts themselves, so all 5 of them. I've also included this file called test1.py that I will quickly use to demonstrate the 2 different ways of calling Python. So in the first method, we can simply go to the command prompt and type in Python test1.py. So you can actually just start to type in the word test1 and hit tab on the keyboard, and it will autofill that file name. So if we hit enter and execute this, it will go through and print hello world and then go through this simple for loop here. Another method of executing this script is to use the interactive mode of Python. So to do this, we first type in IPython, and this will look something like this. From this point, we can type in import test1. This will import this script into our interactive version of Python. And now we can actually type in test1.main to call the main function in test1. So if we execute that, we will get the same output. So let's look into what would happen if we had some type of error in this script. So let's simply change II to JJ here. So we would expect this script to now fail. If we type in python test1.py and try to execute this, we will run into an error that JJ is not defined. But once that happens, we are back into the command prompt and we can't really go in and examine what's going on here. We can't debug this. But if we go back to interactive mode, import this script, and then execute test1.main, we will still get this error, but now we can type in the word debug and it will take us to this environment here. So we are at line 7. We can query the value of II, so we can print II. We see that has the correct value of 0. We can print the value of JJ, which doesn't exist. That gives us our error. So this simply demonstrates that you can quickly execute these Python scripts using just the command prompt, but what may be more helpful to users, and certainly for debugging purposes, will be to use it in the interactive mode. We are now ready to execute the generate microstructures.py script. First, locate the directory with the Dream3D and .json files, as well as the .py files of the 5 scripts. Go up one folder to the main directory and create a new directory called Prisms-Fatigue_tutorial. This is the directory into which we will create the other simulation folders. So if we go back to the Python script on the left, we see this variable dir loc. Dir loc is determined at the top here, and this basically sets the path based on where this generate microstructures.py file is. So in this first line here, what we're saying is that we want to create a new directory. This directory is the combination of dir loc, which is Prisms-Fatigue folder here, but one file up. So this is where the Prisms-Fatigue tutorial will be stored. So users need to create this main folder here, but the Python script will create the cubic tutorial folder. So you'll notice that this folder is empty at this point. Let's set the other parameters. Pick the Dream3D input file with the cubic texture and equiaxed grains. So this file should be available in the Prisms-Fatigue folder. The way I'm specifying the paths here is a way that will work for any set of folders, in the sense that you don't have to set the absolute path. But if users do want to set an absolute path, for instance, the way I'm highlighting it here, that is an option as well. It's just that this option, the way I'm specifying it here, appears to work a little bit better in terms of links getting broken down the line. So we also specified the Dream3D file path and the executable path. Specify the size and shape as such. So shape being 29 elements cubed and the size being 0.0725. Number of elements per subband specified by numvoc should be 8. Number of planes should be 4. And let's specify everything as periodic in all 3 directions. Let's change num instantiations to 5 in this case to create 5 instantiations. Hit save, and now we can go to the command prompt and execute this script. Type in Python generate microstructures into the command prompt and hit enter. The first line that will appear will say current output microstructure file and then print a path to the location of the instantiation. We can check back to this folder here, Prisms-Fatigue tutorial, and now we have a new folder entitled cubic tutorial. If we open that, we will see it begin to be populated with files of instantiations. So in this command prompt, we see 0, 1, 2, 3. We've generated 4 microstructures thus far. It's working on the 5th one right now. Once these finish, it will begin to band and subband the microstructures. It will also display how long it took to perform these operations on each microstructure. As these operations are done, these files will begin to populate the folder we generated. What is especially nice about this type of execution of Dream3D with the Python script is that if we wanted to make 5 instantiations in Dream3D, we would have to open that GUI, the .json file, and not only hit run pipeline 5 times, but we would have to make sure that we number each instantiation properly so as to not overwrite each one of the files. In this way, we don't have to worry about that because all the files that are generated by this Python script are already numbered appropriately. So this takes any kind of user error out of generating the microstructures. Now we see the Python script is complete. The total program took 110 seconds to run, and the majority of that was to create the bands and the subbands over which we will average FIPS. I will now execute this in the interactive mode. So IPython import generate microstructures as gen. So you can say, you can import it as custom name, then we can type in gen main, and this will execute the exact same set of commands as we did just moments ago. What's important to note is that if we execute this multiple times, we actually overwrite all the files in here. So you'll notice that these currently have a timestamp of 1158, but now, since the current time is later than that, all the new files that we generate are going to have a timestamp of 1210. So that is something to be very careful of, is that if you generate these microstructures and run the script with the same folder path as defined up here in directory, you risk overwriting previous microstructures. This may be problematic if you go through the trouble of making microstructures and simulating them and then accidentally rerunning this script with the same directory. Well, now the simulation files you have from crystal plasticity, Prisms-plasticity, they're no longer relevant to these new microstructures because they're new microstructures. So that is something to be very careful of. To remove this risk, a new feature has been added. We simply specify the true or false value of generate new microstructure files variable. If this is set to true, then we will create new microstructure files. However, if this is set to false, then we execute the remainder of the script, but we use the previously generated microstructures. So this will be useful for making sure you don't overwrite the previous files that you instantiated. Additionally, print_params is a function that simply writes all of the settings here to a text file, so you can quickly remember all the settings for this particular set of instantiations. Let's quickly go through what goes on in the rest of this script. So when you execute this script, after you set all your settings, gen_microstructures is the function that is called. And that function is right above the main function. So this function will go through and call other functions and perform many other tasks. It's really difficult for me to go through what every single line does, but I've done my very best to comment every line of code, and I think you'll find it very easy to understand. Let's go over the files that are generated. Not all of these files will be used, but some of them will provide additional information for the users. We mention a filter in the Dream3D pipeline that generates outputs for each grain, so let's look at that. So this file is going to be called feature data fake mat underscore and then some number based on the instantiation. So this one actually has information for every grain. The first number in the file is the number of total grains in the microstructure. And then for each grain, it lists several aspects of that grain, such as orientations in different formats. If we scroll over, we have the centroids. We scroll over further, we have the equivalent diameter. We have the Euler angles, the number of elements, number of neighbors, the phase, and volumes. The grain ID _0 and orientations _0, these are actually the files that will be read in by Prisms-plasticity to execute the crystal plasticity simulations. Now, these files here are used for visualization. The Vtk is one of the first files that is exported when Dream3D creates these microstructures. So if you double click on that, it will open up in Paraview. To view it, click Apply on the left side of the screen. And at this top drop down here, you can navigate to Euler angles, feature IDs, or phases. So feature IDs is actually grain IDs because grains in Dream3D are called features. So then we can view the microstructures that we generated. So this shows us individual grains, but if we click on the drop down and go from surface to surface with edges, we will see the grain IDs in terms of each voxel. So let's close this VTK. But one additional thing about the VTK file is that we can also open it in Notepad++ as a text file. So this is useful because we can read this data into Python and manipulate it further. Each microstructure has a .dream3d and a .xdmf file. So if we double click on the xdmf file, this will also open up in Paraview, and we can actually also view the microstructure instantiation. So this is the exact same information, but depending on the exact filters in Dream3D, you could also export different type of information. For instance, boundary cells specifies what cells or voxels are at the boundaries between two or more grains. The other files give information about grains, bands, and subbands for FIP volume averaging. For instance, element band sets and element grain sets is simply the array of which elements belong to which band and which elements belong to which grain. So this is used by the calculate fips.py script to volume average fips over bands and grains. If we scroll down, the file subband info stores information on the elements in each subband for the same purpose, the purpose of volume averaging fips over subbands. The remaining files simply contain the same information but in text format. So for instance, band set 0 contains the list of what elements belong to what band. So for instance, in line 2, we have what elements belong to grain 1 of plane 1 of layer 5, and so on. Elements per band simply lists for each grain number, for each slip system plane, and then for each layer in that slip system, how many elements belong to that band. Subband regions _0 show us how many elements belong in each subband, but also exactly the element numbers. So here we're seeing that in grain 1, in plane 1, in layer 1, and subband number 1, we have these 8 elements. So this is a nice check too, to make sure that the number of elements per subband specified by the user by numvox actually matches what is generated. So this details all the files that are generated for each microstructure. So we can now go ahead and perform crystal plasticity simulations using the grain ID and orientations ID files. These two sets of files are the only ones necessary moving forward in terms of text files. Users will notice that some text files are larger in size. For instance, the text files that list each elements in each subband are 11 megabytes for a microstructure that is 29 by 29 by 29 elements. For much larger microstructures, these text files get very big. If users are concerned about the size of this text file in particular, there is a section in the subband scheme function in generate microstructures.py. If this variable write to file is set to false, this text file will not be generated, but this .p file will still be generated because the .p file is actually necessary in the volume average fips.py script. This is the grain ID _0 text file, and it simply indicates to which grain each element belongs. Orientations _0 states the grain orientations for each grain. It has 5 columns, and in the last one is where we include the phase of the grain. Now currently, the Prisms-Fatigue workflows only support a single phase, but in the future this will be updated to handle multi-phase materials. The reason the first line has only zeros is because Dream3D has a special placeholder for grain IDs and phase IDs of 0. So the users can ignore this. As part of this tutorial, we will go through the entire Prisms-Fatigue workflow. We will generate and simulate the response of both cubic and random crystallographic textured aluminum 7075. For this, we will generate 5 microstructures of both textures. We already generated 5 with the cubic crystallographic texture previously. So now we will generate an additional 5 with the random crystallographic texture. To do this, change the directory in the generate microstructure script from cubic to random. So executing this now will create a new folder and populate it with new instantiations. We also need to change the Dream3D input file. So we can navigate to the Prisms-Fatigue folder, and we see here that we have another Dream3D file called random texture equiax grains. So if we copy this file name and paste it into our script, we're now ready to generate an additional 5 microstructures with random crystallographic texture. Leave all settings the same. We will create 5 of these microstructures as well, and we will retain the periodic boundary conditions that I will go into next. This command prompt script is still in the interactive mode. So even though we hit save, we imported a previous version of the Python script. If we want to still execute this in interactive mode, we first have to quit and once again type in IPython and re-import the script. But for now, let's just execute it in the simpler way. So let's make sure it creates the folder that we expect. We navigate to the Prisms-Fatigue tutorial folder, and then we can execute this Python script in the command window. So right away, it made the random tutorial folder, and now it will begin to populate it with the files that we need. Let's talk about some final considerations with the microstructures that are generated here. If we look back on the input file, we have 2 tabs at the top of Stats Generator, Primary and Precipitate. Although the Precipitate tab is here, when we click on the gear, we see that the volume fraction is set to 0. On the primary, the volume fraction is 1. So although this tab is here, that doesn't mean we actually have a secondary precipitate phase in our microstructure. This is important because right now the Python script does not distinguish between different phases. So we can have an input file for Dream3D with multiple phases, and the banding and subbanding process will be unchanged. An important limitation of the script is that right now only cubic voxel functionality is supported. This does not mean that users cannot have microstructures that are different shapes. For instance, users can change one of these sizes and change the corresponding shape. So for instance, in the X, this could be set to 20, and then the size in the X needs to be set to 50, because this will still give the same voxel size in that direction. Let's look at the microstructure. If we view this microstructure, we will see that it has a certain number of grains. In this case, the color bar here indicates all the grain features and their numbering, and this goes from 1 to around 240 in this case. So users will wonder how this is specified. Well, in the input file, in the stats generator filter, we specify the log normal grain size distribution. And in this case, the mean grain size is set to around 14 microns. In the size array for generate microstructures, we set the size to 72.5 microns in the X, Y, and Z direction. So then this makes sense that we have around 250 grains. That is what we should expect to fit in this synthetic volume. In this case, each grain consists of about 100 elements. In the setting where we specify the number of elements per subband region, we set this to 8. users will see in the corresponding references that this number of elements corresponds to around 8 to 10% of the grain volume. And the reason for this is that the fatigue crack formation driving force will happen at a subgrain scale. So this is appropriate in terms of how many elements should comprise a subband region. I should note that if numvox is too high, then the subband scheme will turn into the banding scheme. This is because if the number of desired elements per subband region is as high as the number of elements in that band, the two will be the same. Users will find that microstructures with very large number of elements take a long time to undergo the subbanding process. The final item to discuss is face_BC, which controls the boundary conditions of the generated microstructures. As mentioned, the three options include setting these all to periodic, setting these all to free, or setting 2 to periodic and 1 to free. The written tutorial also explains these in depth. The first two options are easiest to understand. When all of these are set to periodic, Dream3D generates microstructures as periodic in all three directions. What this means is that during grain growth and tessellation, if a grain reaches the boundary of the microstructure, it wraps around and grows on the other side, to therefore make a periodic microstructure. If all these options are set to free, then microstructures are generated as non-periodic, which means that as grains grow, once they reach the boundary of the microstructure, they do not wrap around to the other side. Dream3D only has the option to generate microstructures as fully periodic or non-periodic. However, users will see in the references that some simulations are performed with one set of parallel faces set to non-periodic to emulate free surfaces, while the other two directions are still set to fully periodic. For instance, in the slide here, what this indicates is that in the y direction, the simulation is a free surface, while in the z and the x, it is constrained as periodic. So essentially what this would emulate is a thin film or a thin sheet of material. And this does not have any implications for the simulations in terms of how microstructures are generated, but it does affect the subsequent FIP volume averaging. To demonstrate this, let's generate one microstructure in this third option. So we will change the face BC in the y direction to free. Let's create a new folder. So scroll up to directory and let's entitle this free_surface. Let's also change the number of instantiations to 1 since we only need to look at one of these. Hit save, then navigate to the command prompt and execute this updated script. So we expect a new folder in this Prisms-Fatigue tutorial. So let's go there and let's wait for this to finish. So we will notice an additional line in the output, and that is splitting grains across SVE boundary. Now this is very important because we essentially locate the grains that have been split by this now non-periodic face. So let's open up the Vtk file and view this microstructure. And alongside this Vtk, there is an additional text file that is generated. So if we go back on the folder, we see this additional text file and it is called split grains. So this text file identifies the grains split by the non-periodic face. So it says that grains 2, 17, and so on are split by the non-periodic face. So that would be this top surface here and the bottom surface here that are normal in the y direction. So let's see if this is in fact the case. Click on this feature here called Threshold in Paraview, hit Apply. Scroll down to Scalars, and essentially what this does is for feature IDs below a certain number, it lets you hide all the other ones. So let's make sure that grain number 2 is actually split by the SVE boundary in the Y. So this grain is particular in the sense that it wraps around many sides of the SVE. Let's click back on top here and change this from surface to edges to outline, and then open this eye here so we can see where this grain is. So it's at the edge of the microstructure. So this grain is split by the Y face. Another grain that was split by the Y face is grain number 17. So let's go back on Threshold and change this to 17. Hit Apply, and we see that this grain is also split by the SVE boundary in the Y direction. The next one is 32. So we can click and type in 32, and we will see that this one is also split by the Y face. So this actually has no influence on the crystal plasticity simulations that will take place. The Y surface is non-periodic, so this top face and the bottom face are going to act as free surfaces, while in the X and the Z we will have a periodic response. Why this is important is because if we average FIPS over these volumes, we need to recognize that these should be separate grains, because the Y surface is now non-periodic. So what the algorithm does is it identifies all the grains split by the non-periodic face, and it essentially indexes them as new grains solely for the purpose of calculating and volume averaging FIPS. Let's summarize what was discussed in this second video on the generate microstructures.py script. We first went through the installation of Python, Dream3D, and Paraview. We then opened and viewed the Dream3D files, both the pipeline file and one of the input files. We discussed the inputs at the bottom of the main function in the generate microstructures script. Some advanced features of banding and subbanding were discussed. And finally, we generated two ensembles of SVEs of statistical volume elements with cubic and random crystallographic textures. Thank you for your attention, and I'll see you in the next video where we will discuss the calculate fips.py script.